This problem with my socks. Okay, and we had a boundary condition here. We had Dirichlet boundary conditions on the sides. Okay, and then we sort of, the way we did this was sort of separate variables. Then there's these directions this way in the xy plane led to an eigenvalue equations. Okay, so parallel directions. Okay, parallel to what? Parallel to the boundary conditions, the non-trivial boundary conditions. Okay? Parallel directions to boundary conditions. Lead to eigenvalue equations, and then you could expand the initial data in terms of the eigenfunctions of those of the parallel direction. Okay? And then once you've expanded the initial condition of boundary conditions in terms of the eigenfunctions, then you can propagate the data from the boundary into the interior. And so we did all that last time, but that's the idea. So 1 and then 2 propagate. Right. And so we said I've worked out the Green's function to do that last time. Okay. A was proportional to what? E to the minus gamma n z psi n of x psi. Okay, the star has kind of turned out to be irrelevant because the eigenfunctions were real. Okay, so hopefully kind of familiar. I mean, if you write it in terms of quantum mechanics, it kind of looks like u to the gamma and z is kind of. So the propagator looks something like that. Okay, which, except for an I, looks a little bit like that. Okay, and then you insert this propagator in there, and it propagates the data up into the interior. Okay, so we'll do very much the same thing now, somehow in spherical coordinates. Okay. So in spherical coordinates, so let's take this, kind of famous problem, okay, which is just you have a sphere which is neutral, metal sphere. Okay, the sphere has radius A. Famous problem. Neutrals, all radii are always called A. For some reason. Jackson. Okay, Jackson called it A, and everybody calls it A. Okay, so a neutral metal sphere of radius A in an electric field is placed. Okay, so it's placed in a constant electric field. And then what happens, of course, is, when you put it in this electric field, the plus charges move to the top, okay? And since the sphere is neutral, there must be some balancing charges, minus charges on the bottom, okay? And so you induce turns out you induce a dipole moment on the sphere, on the surface of the sphere. Okay? So let's just sort of do this problem together. Right? So first of all, we want to use separation of variables. But let's just state first the boundary conditions that we have. Okay? So first, boundary conditions. Okay, well, the boundary conditions are twofold. Okay, so first, the surface of the sphere, it's a metal sphere, is constant, right? And the potential is constant on this boundary. Otherwise, charges would flow. Phi. So that's the first boundary.
Are we doing this in 2 dimensions?
In 3 dimensions, but there's no azimuthal dependence, right?
Oh, I see.
Right, so kind of simplify the problem a little bit. No azimuthal, right? Okay, so that's the first boundary condition. The second boundary condition comes from somehow the statement that you're in a constant field, right? So if you're in a constant electric field, right, then at least far from the sphere, right, r go to infinity, you should see just a constant electric field, right? And so it says that for r go to infinity, okay, potential phi, okay, corresponds to a constant electric field in the z direction, right? So the potential is minus E naught z, right? So d phi dz is E naught. Okay, and of course we're going to use spherical coordinates here. So you write the z as for r go to infinity minus E naught r cosine theta. Okay, so that's kind of boundary conditions. Okay. So thinking of just a smidge more, right? You would say, well, I could add a constant term there, right? So that's plus constant. There's no, the overall constant in the potential doesn't matter, right? So you could certainly don't need to have it exactly be that. You could add a constant. You can even say a little bit more somehow the boundary conditions, which is so to say we know that so the sphere is neutral, right? So there's no net charge on the sphere, which means the potential from the induced charge, right, falls off faster than 1 over r. I mean, if it was exactly 1 over r, you would get q over 4 pi r at large distances, right? So you know that actually, since it's neutral, plus some correction, which at least falls faster than 1 over r squared. So somehow that's the translation of those words into math, right? Is somehow the neutral part is putting that in there, right? That at least you know there's no charge on the sphere. If there were some charge, it would fall like 1 over r. Since there's no charge, at least it has to fall off faster than that. Okay. Good, and so it's placed in a constant magnetic electric field, and so somehow that's also this statement. Okay, so those are our boundary conditions. Now we got to go solve the equations. Okay. So we're solving the Laplace equation. 0. Since our boundary is spherically symmetric, we use spherical coordinates, right? So again, dependence here, so get an equation for phi that looks like that. Okay, and so if you teach electricity and magnetism in undergraduate quantum mechanics for a long time, you eventually remember the Plossian and spherical coordinates. All right, so anyway, okay, and that's only after you have a broader understanding of general coordinates. Yes.
So in homework, we computed the Green's function of the sphere. Is it not relevant for spherical coordinates? Or I mean, why not implement that kind of thing?
Yeah, so that would be fine. So you could use the Green's function of the sphere. But you could do that. But you have to, you have to construct a Green's function. That would work. It would work just fine. Except the boundary conditions are somehow at infinity, right? So that adds a small wrinkle, but it will work. Okay. But let's stick with this. So let's stick with this, and we'll give an example of constructing the Green's function in spherical coordinates later on. Okay. Where somehow is the best way to proceed. So for instance, if I were to put a charged ring inside of this sphere, then Green's function would be your friend, okay? Because then you would sort of have some charges here, you would need to integrate over this thing, you would need to require certain boundary conditions or something like that, right? So let's stick with this for now, okay? Okay, so we always, actual practice, okay, I have to erase this one. Put this up here. There. So in actual practice, we always switch variables, right? So we use x as cosine theta. Instead of using theta, we use x, okay? And the reason is because the measure is sine theta d theta in spherical coordinates, which is d cosine theta d phi, or dx. Okay, and x is the canonical name for it. Okay, so we take x between -1 to 1. So we're going to use x. This is x equal 1, x equal -1. Okay, good. X equals 0. So once you make this change of variables, right, okay, so Laplacian squared becomes -1/r squared. So we usually use x. Okay, on x big cosine theta. Okay, so first thing we do, right, is we want to separate variables, so we try a solution. Try solutions. So phi is r times some function, which I'll call p of x, because it eventually will be Legendre polynomials. We'll go off with that statement just a second, okay? So we try solutions of this form. So if I plug this into the Laplace equation, so you multiply by r squared to get rid of the overall factor of r squared, and then you get a separated set of equations. one for R and one for P. So it again separates. Okay. And so again, just like last time, the argument's the same, right? If I leave R fixed, then P is constant, okay? And so if I leave X fixed, then R is constant. And so I get some set of equations which look like this here. Let's do the X direction first. Okay, so there's a constant. Okay, and the constant, okay, the constant is going to be, let's call it nu, okay, and let's actually call it nu plus 1. And so, and similarly for R, so once you have this thing, you can also solve for R. So you get two equations, one for R and one for nu, one for P. So kind of two kind of equations. The first will be the Legendre equation. The second is the radial equation for this function R. Okay, so now let's just remember the setup here. So as we'll see, I mean, the requirement will be that nu will have to be an integer, okay? And then once you have solved for nu being an integer, and usually when it's an integer, we call it L, okay? So if it's non-integer, at this point we don't know anything about it, so I wrote nu, okay? Could be real, complex, who knows? Then we use the symbol nu, okay? If it's an integer, and it will be, we call it L. Okay, so let's just see now a little bit why you should expect kind of at least an eigenvalue equation here. So let's just look at this. So at this point, it's just a differential equation. The nu is some number which is yet undetermined. Right? But the picture looks like this. You have this sphere. It has some boundary condition on this point here. So it's a constant. And say, if I look at the data which is parallel to the boundary, that's the theta direction. This is the parallel direction. So it's parallel to where the data is specified. And similarly, there's a boundary condition at infinity, which I can maybe draw as a big circle. Okay? And again, the boundary condition here is that phi is equal to minus E naught r cosine theta. Okay. So again, we sort of see that the parallel directions is the theta directions. Okay. And generally, in the theta, in the directions parallel to where the boundary conditions are specified, you'll get an eigenvalue equation. And now, in the perpendicular direction, which is now the radial direction, you would then propagate this data here, okay, using some propagators. Good. Okay, and so generally, you should always try and ask yourself, where is the data specified, the boundary data, okay? And in the directions which are along the boundary data, you'll get eigenvalue equations, while in the perpendicular direction, you'll get just equations that you need to solve. Very good. So let's see how you get an eigenvalue equation here. So I have to go solve this equation, right? And, well, okay, so the way it works is somehow like this. So looking at this equation, we find singular points. So you look at this differential equation, and you see that there's singular points whenever this thing vanishes. So plus, minus, and 1. Okay? So at that point, if you think about it, like the structure of the differential equation changes. Instead of being second order, it becomes first order. Okay? And so you'll have to analyze the behavior at those points very carefully. Okay? And so typically the way you do this is you substitute a solution, try some x to the power a, okay? And you solve for the power a near the single point. So it's a typical procedure. In this case, if you do that, you go plug it in, you'll get basically what's called the indicial equation. Undergrad, okay? Then you'll get the indicial equation, and you'll solve for a. Try, find, and solve for a. And now in this case, there's a wrinkle in it. Okay, so you define that a is equal to. You always will get two solutions. In this case, you get that the two solutions are degenerate, and furthermore, they're equal to 0. So you plug that in there, and you get 0. Okay, so normally you'll get two solutions, and you'll get two powers. Okay, some a1 and a2, and the solution will behave like a power near the regular singular points. Okay, but in specific cases, this could be an integer. Okay, and what it means is that one of the solutions is the integer, okay, and the other solution is sort of the degenerate form. It says that the analysis, local analysis, says that this solution behaves like a constant. That's one of those roots, plus another one, which turns out to be log. So log is kind of almost constant, right? So if I take the limit that a goes to 0, instead, the way you can think about it is like this. You have two solutions. You could imagine that that a is very, very small, okay, and take the limit that a goes to 0, and then you will. So the singular point is at x equal 1. And so you plug in that. Okay? So you know that the local solution behaves like this. Okay? That's just coming from this differential equation. And, okay, and similarly, let's keep it up.
Where do we plug in this 1 minus x to the a?
Yeah, you plug it in here. So
Or in place of p?
Yeah. So P has this, I'm analyzing this differential equation. I'm given a differential equation. I just analyze it, right? And the first thing, how you analyze differential equations, you first ask about the singular points, right? And I see that the singular points are at this x equal plus minus 1. And it almost always happens when this P of x, in the notation of last time, goes to 0. Okay, and so I see that happens, those plus minus 1 are singular points, and there I try a power law solution of this form, okay, and solve for the powers, and in this case you get sort of two powers. One is a constant, and the other one is a log, okay, which can be thought as a limit. Okay. So now we have the two solutions, okay, and then we got to do the same thing at x equal minus 1. Analyze x equal 1. And similarly, Okay, the equations are symmetric. Okay, so you get that phi is some constant d1. Right, I call it c1 bar. Plus x, something like that. All right. All right, so that's the general solution right near the singularities, the 1 minus x. And then you start to say, well, you know, what does a singularity mean? Okay. In this case, there's no real singularity there. So, and just our coordinates of the sphere are very well badly behaved right at those points, right? Okay, so x equal 1 and x equal minus 1, you have what's, you know, the singularity arises because your coordinate system is badly behaved at that point, okay? So those are coordinate singularities, okay? So typically what you want to do is demand, okay, that these are 0. Demand regularity at those points. So I'm going to erase this now. Good. So I'm going to put there x equal 1 and x equal minus 1. And so now I'm going to have two boundary conditions, one of which says that it's regular at the top of the sphere, and one of which says that it's regular at the bottom of the sphere. Okay? Okay, if I multiply the solution by a constant, these boundary conditions, I still have a regular solution. So the solutions themselves are, the boundary conditions themselves are again homogeneous in the sense that if I multiply the solution by a constant, you know, I don't change the boundary conditions. Okay. And so now I'm sort of in a situation where the problem is somehow over-specified. I have a boundary condition here at x equal 1, and I have a boundary condition here at x equal minus 1, right? And in general, and the overall constant in the solution doesn't matter, so the problem is actually over-specified, right? And so the only way out is to adjust the value of nu, to adjust in the equation I just raised. Okay, to satisfy boundary conditions. Okay. So at that point, it really does become a kind of eigenvalue problem, where nu is not arbitrary, but is chosen, adjusted, so that you can reach these two boundary conditions. Okay. Good. So now we have really an eigenvalue equation. Okay. So let's just look at it. So now it's an equation, it's not just a differential equation anymore, but it's actually an equation both for the function and for the constant nu, an eigenvalue equation. And if you look at it, this L of x, this operator, which is this one, is precisely a kind of homogeneous of Sturm-Liouville form. So this is exactly the sort of Sturm-Liouville eigenvalue problem that we talked about. Okay? So let's just see let's just see whether the operator itself is self-adjoint. Okay? So check. Self-adjoint. Okay, so let's just see. There's some. So what do we mean? Okay, we mean that if I integrate over the measure, if I take any two functions, f and g, which satisfy the boundary conditions, okay, so that's important, right? Then if it's self-adjoint, we mean that it satisfies the following equation. Good. So let's just check that it is actually self-adjoint. So if I plug this in here, right, do this thing, right, what I want to do is integrate by parts twice and move it onto there, right? And that's how you check whether something's self-adjoint. So integrating twice by parts, okay, you will find the following. Okay. 1 minus x squared. What always arises there is this Wronskian. Of the two functions. So L of x acting on G. So, and of course, this is boundary condition. Okay. So we need to actually if it's going to be self-adjoint, right, we need these boundary terms to vanish, right? And generically, well, you see you have 1 minus x squared there sitting. So it's going to vanish, right, provided that f and g are regular, right? So if you had these logarithms there, right, then it would not be self-adjoint because the derivative of a log would give you 1 over x, 1 over 1 plus x. And then this thing would not go to 0 as x goes to plus or minus 1. Okay, so provided you're regular, okay. That would mean no log. Good. All right. Okay, so now we're back to solving this equation. L of x is given by this operator. You have to find this constant. Okay, you need to adjust the you need to dial the constant nu such that the solution is regular. So let's see how that works. So just a little tiny bit. Okay. So. So, okay, so let me first state the solution. Okay, so it turns out that the constants are constant. Nu is an integer, 0, 1, 2, 3. Okay, and the solutions are PL of x, which are polynomials. Okay, which are 1, x, okay, 3 halves. Different, I get you all see them. Okay, Legendre polynomials, 1x, 3x, x squared minus 1. I don't know any higher. The only ones I know by heart are those. Okay, good. Okay, so, but let's just phrase it as a numerical problem. Like, how would I determine that nu is an integer? Okay. So it would go something like this. Okay, so this is set up just a sketch. Right? So let's keep Okay, this is kind of rough outline of how it works. Okay, so it works for all, same for all Schrodinger equations. Okay, so you choose new random, basically. I mean, you can be a little more clever. Let's just say you have to choose some new. Okay, and now I analyze the differential equation near x equal 1. Top of the sphere. It's not, we already said it, p nu of x is equal to some constant, which we can choose to be 1, and now you can develop a Taylor series. Okay, so the lowest term we already said was 1, or log, which we eliminate. Okay, and now we look at the next term in the series, which turns out to be nu plus 1, 2, 1 plus x, is x. That's just one term. Of course, there's higher terms. O1 minus x squared and so forth. Right near the top of the sphere. Just develop a little Taylor series of this differential equation and solve it order by order. You can find a little Taylor series for this function on the sphere. Okay. So now, you now know, since you've done some analysis, you know the value of the function and you know its first derivative, right? So you can ask your computer to go solve for the function from the top of the sphere to the bottom of the sphere, okay? And the slope was chosen by you. So now you integrate, use your computer, or you can do it analytically too, but let's do it numerically. Use your computer, okay, and you'll adjust this value of this slope, okay? So that's where this sheet comes in, so if you can look at this sheet, I have this sheet. Okay, so it's very much like all Schrodinger equations. I have one more copy. Okay. Right? So it's like all Schrodinger equations, like you dial the energy. Okay, so here's like, let's look at the first plot, right? The first panel. You know, so if I look at what's happening there, if I take nu equal -4, negative 0.4, then the slope is positive. Right? Now I integrate my differential equation. Everyone looking at the first panel here, right? First panel. You look at the first panel, you're dialing the slope. Okay, if you choose a negative, right, then it would go upwards, and then you sort of go up, and by the time you get, if you start at x equal 1, by the time you get to x equal -1, integrating the differential equation, okay, the solution will diverge. Okay, so you're inclined to sort of lower nu, so you sort of reach a sort of regular solution on the other side. Okay, so lowering nu to 0, you finally get a solution which is constant, okay, which is the first Legendre polynomial. Okay, now again, if I lower it further, sort of increase nu a little bit further to 0.4, then I shoot off in the other direction. Okay, to the negative infinity here at x equal 1. That's no good either. Well, no good. You don't know. What I'm plotting here is the Legendre polynomial is for any value of nu, not necessarily. Legendre function, sorry. Legendre function for any value of nu, not necessarily an integer. Okay? So it's certainly a useful function. But for our purposes, we want regularity at the boundary. So I start at 0.4, it's no good. I increase it to 0.6, looks a little bit better. That's the second panel, right? And then if I increase it all the way to nu equal 1, right? It becomes well behaved at x equal -1 again. Okay? So it's a kind of classic sort of shooting problem. And all eigenvalue problems are sort of phrased in this way. Yeah.
So I'm confused as to what exactly the boundary condition is for these p nu's. I mean, like you say it has to be regular at the boundary, but that seems vague, or is
No,
it
because
not?
it's not right, because it's a singular point, and you know that the two solutions of the differential equation are either a constant or a logarithm of 1 minus x, right? And you don't want the logarithm, so you're requiring, you always have two solutions of the differential equation, and you're requiring that I don't have one of them, right? That is a perfectly well-defined boundary condition. So, good. And so that leads then to sort of this quantization that L is this quantized variable. Okay. Good. So now, once you've solved, so now we've sort of handled the angular direction. It's just like Schrodinger equation, except nu is now now I can go ahead and solve the radial direction. Okay, so we've handled this thing. Erase this one. So let's go back and look at the radial direction. So let me erase this. Okay, so just okay, so now I go back to the radial equation. Okay, so the equation is so this again now is not an eigenvalue equation, right? It's just an ordinary differential equation with a specified parameter L, okay? L is some integer. And now I can go ahead, this equation you can just go ahead and solve, okay? Solve, okay? It's homogeneous, okay? Meaning that if you multiply it by a constant, you get still a solution, so you're going to try some power r to the a. Okay, and it turns out in this case that a is equal to plus L and minus L plus 1. So the two solutions, you get two solutions to the differential equation. So RL is some constant, say AL, R to the L, plus QL. R to the L plus 1. That's the general solution to this differential equation. Good. So putting it all together, you have a general solution. Sum over L, okay. A to the L, R to the L plus 1. L plus 1. Some eigenfunctions in the theta direction, which are the Legendre polynomials. Okay, so now we have this general form. Okay, so now it remains to sort of adjust. That's a very general solution. Okay, for any problem with azimuthal symmetry. So we only need to now adjust the coefficients a and b so that you can match all the boundary data. You're guaranteed to be able to do that because the Legendre polynomials are a complete set of functions. Okay? So again, if I look at my solutions, okay, I'm looking here for a potential which is constant on this surface, a potential which is phi, which behaves like cosine theta on the top surface. So you could ask, my boundary data, right, is 1 at r equal a and 1 at r equal, is one proportional to a constant, and one of which is proportional to cosine theta. And so my boundary data only has two, if I think about what I need to, which Legendre polynomials I need to have to express this boundary data. You see that I only need the L equals 0 Legendre polynomial, which is a constant, and the L equal 1 Legendre polynomial, which is cosine theta. Okay? So boundary conditions have only L equals 0, okay, and L equals 1. Like that? Okay, and since the boundary conditions only have L equals 0 and L equal 1, the solution will only have L equals 0 and L equal 1. Solution is a combination, yeah? So phi is some A plus B, A0, B0 for R, plus a constant times 1, plus a constant A1 R plus B1 R squared times cosine theta. Okay, so that's so far things are looking much better. Okay, so now we need to adjust these constants to match all the boundary data. Okay, we already made some choices there. So let's do that. Okay, so first let's look at infinity. Okay, so okay, it's still on the board. You know, as r goes to infinity, the solution has to take this form: minus e naught r cosine theta plus a constant plus something which is of order 1 over r squared at least. Okay, and so as r goes to infinity, that fixes some of these coefficients, right? So as r goes to infinity, I drop these b's as well, okay? So as r goes to infinity, I get fine. Okay. A0 is undetermined, but B0 is 0. Okay, A1 is comparison. Look at there. Here. Right? So A1 is minus E naught cosine E naught. Okay, good. And that's all we can say. Okay? The B naught has to be 0, otherwise it would fall like 1 over R, right? And that would be the Coulomb term. But so that's from the boundary condition 2. Okay. And now from boundary condition 1, of course, on the surface, you need that phi is a constant. So let me put in the known data. Okay, here, this is minus E. I'll leave it as A1. Okay, A1 is minus E. Okay. On surface, phi equal A, phi, and this phi naught. And that fixes the remaining terms, okay? So it's got to be a constant independent of angle, which means that this coefficient needs to vanish on the surface of the sphere. Okay, the A1 plus B1. Okay, and so you get A1 times A plus B1 over A squared is 0. Okay, and you get that A0 is equal to phi naught. And that fixes all the remaining coefficients, so you can go ahead and work out the solution. So the final solution. Problem. So phi is equal to some constant phi naught. And then we get minus E naught. Minus E naught R. And I can solve for B, which is E naught A cubed over R squared. Okay, times the cosine. All right, so that's somehow the answer for the potential everywhere. Okay, so let's just analyze it just 1 second here. Okay, so it looks like this, right? here's the sphere, okay? The potential, compare, okay, compare. So if I go far away, okay, phi is minus E naught, okay. So if I had just a dipole moment, I would find the following behavior. So of course, if I look at the potential far away, so r goes to infinity, then whatever is the charge distribution on the sphere, it must match on to the multipole expansion. Okay, so these first couple terms, right, the phi naught and a constant, okay, those are kind of external, right? But the remaining terms are due to the charges induced on the sphere. And in principle, though it doesn't happen in this case, there could be higher terms in the multiple expansion, okay? Involving the quadrupole moment of this charge distribution and so on, okay? Now what we see from this solution, right, is that actually there is no quadrupole distribution, right? The only term that arises in this multiple expansion is this induced dipole moment, okay? And we can actually read off its value from this coefficient, okay? So comparison with this and this, okay, needs to do it here. Shows that the induced dipole moment says that P is 4 pi cubed provided it's in the z hat direction. Okay. Good. Okay, so what happens is you return this electric field, you separate the charges plus and minus, okay, you get some charge distribution plus and minus. You could analyze what the multiple expansion of that charge distribution is, okay? And you're guaranteed from the multiple expansion that it will take this formula. The external field plus an induced field. The induced field you could always expand in multipoles, like dipole moment, quadrupole moment, and so forth. Okay? And then if I compare this with the solution, we see that the only term that arises is actually the dipole moment proportional to cosine theta. Okay? And the quadrupole moment and so forth is 0. 0 and higher. All 0. Okay, so you just induce a dipole moment, that's it. Yeah.
It does have a term with P moment. Right.
Where is it?
It does have a term with like the electric field.
Sorry. Just compare this and this, okay? So this is, let me write this out as P times cosine theta. So if I used vector notation, but it's actually P cosine theta. So now if I compare this term with that term, right, you see that the dipole moment is actually this thing with an E naught, induced. Okay, very good. Okay, but all other induced moments are 0. And okay, so that's a kind of helpful solution. Next time we'll do Green's functions in spherical coordinates. We do the multiple expansion.